Hello, Calculus. I'm going to take notes today on section 4.1, which is Extrema on an interval. So throughout the video, whenever I scroll down to the next page, just make sure you're pausing the video so you have time to copy down the questions or the notes or the graphs. So we're going to start off with determining what is extrema and what's the difference between relative extrema versus absolute extrema, which is somewhat of a review from pre-calc. And then I'm going to define what a critical number is, because that's going to allow us to find out how to find absolute extrema for a function without just looking at a graph. So extrema is defined, the extrema of a function on an interval are the maxes and minimums on that interval. The definition we'll use, f of c we call a maximum on an interval if f of c is greater than or equal to all the other values of the function on a given interval. And f of c is a minimum on an interval if f of c is less than or equal to f of x for all x on that interval. And f of c must be defined to be an extrema. So if I have an interval from, let's say, -1 to 6, then at this point, we have an extrema here. I'm going to call that f of c. This is an absolute or relative max. Amongst all the points in this interval, this is the highest point. Here we have a relative minimum amongst all the points in this interval from 6 to -1. This is the lowest of all of them. We'll look at two types of extrema, the absolute and the relative. And so the main difference here is absolute extrema are the max and mins on the entire given interval. Endpoints can be absolute extrema, so the endpoints can count. When we're talking about relative extrema, the max and mins on a small open interval, endpoints cannot be considered relative extrema. So think of the hills and the valleys. There could be many relative extrema on a given interval. So if I look at the interval from -1 to 2, I want to find the absolute extrema. So the absolute extrema are the maxes and mins. So I'm looking for the absolute max, and I'm looking for an absolute minimum. In this interval right here, the absolute max is going to be the highest point, and in absolute extrema, you can count the endpoints. So if I'm including the endpoints, then the absolute max is 5. More specifically, it's the point 2, 5. The absolute minimum is the smallest point, which is the smallest value of the function is 1. That's at the point 0, 1. So that's our absolute max, and that's our absolute min. The absolute max of this function, well, we don't actually get to 5. It gets infinitely close to 5. So you can go to 4.9, you can go to 4.99, you can go to 4.999, but you never have an absolute max. So it does not exist. There is no absolute max on this interval. The absolute minimum still, however, does exist and is 1. Or more specifically, it's the point 1, 0, because I like to have the point. Excuse me, 0, 1. Give this one a try on your own. The absolute max, still the point 25. 5 is the absolute max. The absolute minimum, this one does not exist because it never actually gets close to 1. It gets to 1.1, 1.101, 1.001, 1.0001, but it'll never actually hit 1. So there is no absolute minimum. Now, the extreme value theorem, you don't have to pay too much attention to it. I do want you to write it down. It's something that if you take calc again, you'll have to talk more about. But the extreme value theorem is just stating that as long as you have a continuous function on a closed interval, then the function has to have a max or a min. So some functions have maxes and mins, some don't. But on a closed interval, as long as your function is continuous, it's got to happen. So if I'm on some interval from a to b, my function's got to be continuous. So there's no asymptotes, there's no breaks, there's no holes. Who knows what it's doing in between. But if I have a continuous function from a to b, there's got to be an absolute max or min somewhere. In this case, the max is up here at the top, and the minimum would be down here in the bottom. So it doesn't tell you how to find the extreme. It just tells you that they exist as long as the function is continuous on that closed interval. All right. So relative extrema. This is the one where we cannot include endpoints. So the relative max the maximum before is here, but this is an endpoint, so we can't consider that a relative max. So it's not a relative extrema. So there is no actual relative max. The relative min, though, this is not an endpoint. We can't consider that a relative min. Again, think your hills and valleys. If I have my minimums and maximums in local areas are going to be my relative extrema. Okay. Now the relative max here, again, we can't use endpoints, but this is not an endpoint. This is just one of my hills. So that is 0, specifically the point 2 comma 0. That's my max. Again, we can't use the endpoint for minimums, but this is a local minimum, a relative minimum in that interval. Amongst all the points in the little neighborhood around it, it's the smallest. So I'm going to eyeball negative 1.2-ish is what I'll say it is. So that's the point. It looks like it's maybe 3.3 comma negative 1.2. If I were to make it a coordinate. So that's the relative min. Now this function here, you can give it a try on your own. But the max right there is 0. It's the point 0, 0. And the relative min, there's actually 2 of them. So we have negative 0.75-ish, comma negative 0.25-ish. And we have positive 0.75 and negative 0.25-ish. So we have 2 relative minimums there. And they both happen to be the same value of negative 1/4. Okay, so graphically, it's pretty quick to find out where the max and mins are. To do it analytically, we have to first define a critical number and then use this idea to find where maxes and mins occur. So now that you've copied it down, let f of x be defined at c as long as this is true. This is like the prerequisite. As long as the function is defined at c, then the function has a critical point at c if the derivative at c is 0 or the derivative at c does not exist. All relative extrema occur at critical numbers, but not all critical numbers give relative extrema. So what that means is if you have a relative max or a relative min, at that point, the derivative of the function has to either be 0 or the derivative of the function or the slope of the function does not exist. But just because the derivative of 0 does not exist doesn't guarantee that we have a max or min. But if we do have a max or min, it's got to be at one of those points. We'll look at how to find relative extrema analytically a little bit later. So what does it look like when the derivative does not exist? Well, if there's asymptotes, if the function itself doesn't exist, the derivative certainly doesn't exist. But not only that, but when you have these sharp turns in functions, like the absolute value function, or if you have something like this going on, at these corner points, the derivative does not exist. So that's what it looks like visually when you have sharp turns. And the reason why is if you think of the derivative as the slope, and do you remember the slope started off as a limit? Right? The limit as h approaches 0 of f of x plus h minus f of x over h. So if I take the slope, which remember, the derivative is the slope from the left side. The slope from the left side is negative 1. If I take the slope from the right side, the slope is positive 1. And in order for a limit to exist, the limit from the left and the limit from the right need to be the same. However, here the limit from the left is negative 1 and the limit from the right is positive 1. So in this case, the limit would not exist, so the slope itself does not exist. Okay, so here's an example of when the derivative does not exist. This is what it might look like. Now, I said before, if we have a max or min, it's got to be at a critical number. So before when I said, does the function have any horizontal or vertical tangent lines, what we would do is we would find out when the derivative equals 0. That tells me where my maxes and my mins are, is when I have my vertical, when I have my horizontal tangent lines when the derivative is 0. Now, just because the derivative is 0 doesn't guarantee you have a max or a min, because in this situation, the derivative of the function at 0, the slope of this function at 0, is 0. So here the derivative is 0, but 0 is not a critical number. is not a relative extrema. Whereas, say this was the point, I don't know, 1 and 2. The slope at 1 is 0. We have a horizontal tangent line. And the slope at 2 is 0. We have a horizontal tangent line. So x equals 1 and x equals 2 would be critical numbers. All right, but just because we have a critical number, we could have this situation where we don't necessarily have a max or a min. So, how to find an absolute extrema analytically. Copy this down, and I'm going to follow these steps in the next example. So you're going to come down here and copy this example as well. And going back to the top, to find out where the function has absolute extrema, we want to find the critical numbers, because if there's relative extrema, it's got to occur at a critical number. Again, I'm finding absolute extrema, so endpoints are allowed. So once I find my critical numbers, I'm going to find the value of my function at the critical numbers, because that's where my relative extrema could be. But then I also want to find the value of the function at the endpoint. So I'm going to plug in A and B to find out if those are greater or less than the value of the function at the endpoints. So where the function is the smallest is the minimum, and where the function is the greatest is the max. So step 1, we want to find the critical numbers. So we need to find the derivative of the function and find out where that 0 does not exist. So the derivative, we get 12x cubed minus 12x squared. Now the derivative is a cubic function, so the derivative exists everywhere. There's not going to be any place where the derivative does not exist, because cubic functions are continuous everywhere. But I can find out where does the derivative equal 0. So what I'm going to do is I'm going to set it equal to 0. I'm going to factor the 12x squared out. So I get x minus 1. So if 12x squared times x minus 1 equals 0, then either 12x squared has to equal 0, or x minus 1 has to equal 0, which means x has to either equal 0 or x has to equal positive 1. Because my original function is a degree 4 polynomial, it's defined everywhere, so the function does exist at 0 and 1, and the derivative is 0 at these points. So these are my critical numbers. Okay. So we found the critical numbers. Now we need to evaluate the function at each critical number and endpoint. So I'm just going to make a table here. So if I have a relative extrema, it's going to be at 0 or 1. I might have a relative max or relative min. I could also have max or absolute extrema at my endpoint. So I got to check -1 might be a max and 2 might be a max. So if I plug these numbers into my function, that'll tell me where my highest value is and where my lowest value is. So we got to plug -1 in, plug 0 in, plug positive 1 in, and plug 2 in. If I plug -1 in here, that's 3 times -1 to the 4th minus 4 times -1 cubed, which is going to be 3. -1 cubed is still a negative. The double negative will make that a positive 4, which would give me 7. If I plug 0 in, that'll give me 0 minus 0, which equals 0. If I plug 1 in, that becomes 3 minus 4, which is -1. And if I plug 2 in, 3 times 2 to the 4th minus 4 times 2 to the 3rd. I think that gives me 16. So the absolute max is going to be the smallest value, and the absolute the absolute minimum is going to be the smallest value of the function, and the greatest one is going to be my absolute max. So here's my function. The smallest value is here, so we have an absolute minimum here. The greatest value is 16. That's going to be my absolute max. Okay. So the absolute min is -1. I'm going to write, it's the point 1, -1, where -1 itself is the smallest value the function takes in that interval. The absolute max is the greatest value my function takes in that interval, which is 16. That's going to be the point 2, 16. And that's where we find our absolute extrema. Copy down another example. Again, step 1, find the critical numbers of the function. So that's when the derivative is 0 does not exist. The derivative is going to be 2 minus 2x to the, let's see, 2/3 minus 1 is negative 1/3. Again, just using the power rule. 2/3 times 3 is 6/3. 6/3 is just 2. So we got to find out where the derivative is 0 and where the derivative does not exist. So let's find out where it's 0. Let's see. I'm going to subtract 2 on both sides. So I get negative 2 equals negative 2x to the negative 1/3. Divide both sides by negative 2. So I get positive 1 equals x to the negative 1/3. This is equivalent to 1 over x to the positive 1/3. Multiply both sides by x to the 1/3. I mean, the answer might be obvious for you at this point, but I'm going to do it all algebraically. 1 times x to the 1/3 is x to the 1/3. How do I undo taking the number to the 1/3? I'm going to raise it to the third power. So those undo each other. So we get x equals 1 cubed, which is just 1. So as long as x equals 1 is defined in my original function, it's a critical number. And yes, if I plug in 1, I get 2 minus 3, which is negative 1, which exists. So that is a critical number. Now I want to find out, does the derivative not exist anywhere? And it actually does. If I look at this function, 2 minus 2x to the negative 1/3, the negative 1/3 is equivalent to 2, so 2x to the negative 1/3 is equivalent to 2 over x to the positive 1/3. And we can't divide by 0, so x can't be 0 here. If x were to be 0, we'd be dividing by 0, which would be undefined. So the derivative does not exist at 0. Because if I put a 0 in here, we're dividing by 0, and then we're in trouble. Is f of 0 exist? And yes, if I plug 0 in, 0 to the 2/3 is 0, times 3 is 0, 2 times 0 is also 0, and we get 0 minus 0, which is 0. So this is 0 does exist in my original function, but it doesn't exist in the derivative. So this is also a critical number. All right, so we have 1 and 0. So we got to make our table to find out where our absolute extrema are. Now, the absolute extrema are either at the critical numbers or at the endpoint. So we have negative 1, we have 0, we have positive 1, and we have 3. If I plug these into my original function, the smallest one is going to be the absolute min, and the greatest one is going to be the absolute max. Okay, so we plug negative 1 in, that becomes 2 times negative 1 minus 3 times negative 1 to the 2/3. Remember, plug these numbers into the original function, not the derivative. So that becomes negative 2, negative 1 squared is 1, the cube root of that is 1, so that's negative 3. So that gives me negative 5. If I plug 0 into my original function, that becomes 0, 0 to the 2/3 is 0, times 3 is 0, so 0 minus 0 is 0. If I plug 1 in, I get 2 times 1 minus 3 times 1 to the 2/3, which is 2 minus 1 to the 2 is 1, so 2 minus 3 is negative 1. And if you plug 3 into the original function, I got about negative 0.24, I believe. Negative 0.24-ish. So the absolute max is my highest point here, which is 0. That's greater than all the negative numbers. So that's my absolute max. My absolute min is the lowest value here. The smallest value or the least value is the negative 5. That's my absolute min. So my absolute min is at negative 1, negative 5. It's negative 5 itself. The absolute max is 0, 0. That's the second 0. That's my absolute max in the function on the interval negative 1 to 3. Okay. Quick little thing. If I had a critical number, say I solved this part here and I got x equals 1 or x equals, 6. 6 could be a max or a min, but if it's outside of an interval, I'm not going to test it because I'm not interested on values outside of the interval. So if you ever get a value that's outside of your interval, you don't really have to worry about it. Anyways, that's all for relative extrema. We're going to get more practice and we'll get more time on the theory of why this works. It's going to come up throughout the chapter. So this is just to get kind of a brief idea. We'll get some reps in class and we'll get a little bit better. But if you like the video, make sure to leave a comment. ring the bell for notifications, and smash the like button if you liked it.